Hello astronomers, welcome back. This week we're going to be talking about how we measure properties of the stars. So that includes their apparent brightness, their actual brightness, their temperatures, sizes, luminosities, their masses, those sorts of things. One of the most important things we need to get down before we can figure out the properties of stars is how to determine how far away they are. That's primarily because of the brightness of the stars. It's hard to determine if we don't know how far away they are. If something's really bright but very far away, that means its intrinsic luminosity is extremely high, as opposed to something that's really bright and close, could be intrinsically quite faint, but it just happens to be closest to us. So distance is important for figuring out the properties of stars, so that's what we're going to be talking about today. And because we don't, today we can go look up in a book the distances to all the stars, distance to the sun, the planets. But before we had those books, it was very difficult to know those things. We had to kind of bootstrap our way up observationally to figure out how far away things are. So we're going to start with something that folks call the distance ladder. So this is determining the sizes of objects, and we're going to move out until we have an idea of the size of the solar system and then the distances to the nearest stars. Interesting thing about this is that these are observations that you can make yourself. If you think about the technology that was available to people making these observations, it wasn't super advanced. In fact, the first measurement was made using a stick. So these are measurements that you can make yourself, something that's I think pretty cool that you can go out and do that. Later on, we'll be making measurements that require advanced telescopes, and that's something that we need to have a society that builds this big instrumentation to do. But a lot of these things you can make observations on your own. Okay, so let's get started. What we're looking at here is Stellarium, and Stellarium is, can I get rid of that? Yeah, okay. So what we're looking at right now is a scene from Stellarium. This is actually back in June of 2020. And I picked this date because it's very close to the summer solstice, which means the sun is highest in the sky. And this is at about the time when the sun is highest in the sky. You'll notice that's not happening at noon, and that's because of the fact that we're on daylight savings time, which sets us back an hour. We're not in the middle of our time zone, so that adjusts the period. But you can wait until the sun gets as high as it can be in the sky to make these types of observations. And one of the things we can do in Stellarium is we can select the sun and get an observation of how high it is in the sky. This is showing us that the sun from Ogden, Utah, on the summer solstice has an altitude of about 72 degrees. So that's a measurement that you can make in a number of ways. The most difficult way is to use your fists, like we've done with the North Star. That's challenging because you don't want to look directly at the sun, but you can put a stick in the ground, you can measure the length of the shadow, and from a little trigonometry you can figure out how high the sun is off the horizon. But what I'm really trying to show you is that this does not stay the same depending on where you happen to be on the Earth, and that's because the Earth is round. So if we were to travel to the south, if you travel to the south on a round globe, that means you're moving to a point that is closer to the point directly beneath the sun, and that means the sun should look like it gets higher in the sky. So we can do that in Stellarium. I can come down here and I can go to my location window, and let's choose some place that's easy to drive to, like Provo. So then we can see that the altitude of the sun has changed. It's now a little bit higher than 73 degrees. So we've driven south by the distance between Ogden and Provo, and that's made the sun rise in the sky by about 1 degree. What that means is that the distance that we've traveled along the Earth is about 1/360th of the entire circumference of the Earth. And so this is a measurement that if you can know the distance between Ogden and Provo, you can figure out the entire circumference of the Earth. And the Greeks, in particular, a Greek by the name of Eratosthenes, made this measurement several thousand years ago and came up with a pretty good estimate of the size of the Earth. So making this measurement allows us to get the size of the Earth, and once we know the size of the Earth, then that's our first building block to bootstrap in our way up into the solar system. Okay, so that's number one, size of the Earth. The second measurements we made is to try to figure out how big the moon is. Now, we don't know how far away the moon is to start off, so what we would like to do is we'd like to measure the size of the moon, and then we could measure how big the moon appears to be, and that would give us the distance between the Earth and the moon. So the only thing we know is the size of the Earth, but if we could be in a configuration where the shadow of the Earth was passing over the moon, we could figure out the size of the moon relative to the shadow of the Earth. And because we now know the size of the Earth, we would then know the size of the moon. So you can do that by waiting for an eclipse, a lunar eclipse, and measuring the size of the moon. Once you know the size of the moon, then you know how far away it is, because we can measure how big it appears, and we can work that out. So the size of the Earth gives us the size of the moon. The size of the moon gives us the distance from the Earth to the moon. Okay, so now what I want to do is I'm going to focus in on the moon here, and we're going to make another measurement to try and get the distance between the Earth and the sun. So what do we know? We now know the distance between the Earth and the moon. So if we could set up a triangle such that one side was the side between the Earth and the moon, and we could make a 90-degree triangle so that we could just measure one other angle, then we could figure out how far away the sun is. So let's make this configuration in Stellarium to see what this looks like. So the way I want to do this is I want to get a 90-degree angle between the line between us and the moon and the sun. Okay, and we can do that by moving the moon to a third or first quarter phase. So I'm going to see if I can do that here. Just marching through. I'd like to center on the moon here. There we go. And we're just going to march through, and let me zoom in and make sure we can see this here. Let's see where we get. Oh, it's not letting me track it. Okay, so we're almost there. Let's go put the moon a little bit higher in the sky. Too high. There we go. So we're almost to a half lit moon. What do you think? One more day maybe? Let's see. There we go. Oh, where'd it go? Okay. So there's our half lit moon. You can see that the bright part is visible from us exactly half, which means that the sun is directly away from the lit half of the moon. So let me zoom out and see if we can see where the sun is, because the sun is still visible in the sky here. There it is. Okay. So we have the sun and the moon, and we're in a configuration now where the moon is, the line between the sun and the moon and us is 90 degrees. So that means if I've got a line from the sun to the moon to the Earth, if I can measure the angle between the moon and the sun, then I can get an estimate of that other side of this triangle using trigonometry. All right, so to show this measurement, I'm going to have to do something a little contrived, and what I've done here is I've removed the atmosphere so that we can actually see the sun and the moon at the time that we have the configuration we just talked about. So let's zoom in on the moon here just to make sure we can see that it's half illuminated. Okay, so we have half illuminated. Here is the sun right there, and we are the Earth, right? So you can imagine a line going from me to the sun. There's a line going from the sun to the moon, and then that's a 90-degree angle back to me. All right, so that's a picture where if I can then measure this angle between the moon and the sun, then I should be able to figure out the other sides of the triangle. So if I click on that measuring tool and I click on the moon, and then I go over here, we're going to find out that the sun is not quite 90 degrees away. So the sun, this angle between the moon and the sun on the sky is almost, but not quite 90 degrees. So I want you to take for a minute and draw on a sheet of paper, put the sun the Earth and the Moon and try to make a triangle where one angle is 90 degrees and the other angle is 89.5 degrees, and how big you'd have to make that. It turns out the sun is really far away. In fact, it's effectively infinitely away. For all intents and purposes, we can just assume the rays hit us in parallel lines, but they're not quite parallel. One's coming into the moon at 90 degrees, one's coming into us at 89.5, and you can try to draw that picture and see what you get there. But those observations allow us to determine how far away the sun is. And it turns out the sun is really, really far away compared to the moon. I can only imagine how this must have blown people's minds when they first made this measurement, because the moon and the sun are more or less the same size on the sky. One happens to be really bright, so you wouldn't necessarily think the really bright one would be really far away. So that gives us that measurement. It turns out, just to give you some perspective of how much further away the sun is, it takes about 1.5 seconds for light to reach the moon. It takes about 8.5 minutes for light to reach the sun. So that gives you an idea of how far away the sun is compared to the moon. Okay, but once we know the distance to the sun, that fixes our astronomical unit. And as we learned a little while ago, once you have the astronomical unit, then you can figure out the distances to all the other planets thanks to Kepler. So now we know the distance out to the planets, that any planet you can see with your naked eye, and any other planet we discover with a telescope that we can't see with our naked eye. We now know the size of the entire solar system. So again, just to recap, we have the figuring out the size of the Earth. That helps us figure out the size of the moon. Once we know the size of the moon, we can figure out the distance to the moon. Once we know the distance to the moon, we can figure out the distance to the sun. And once we know the distance to the sun, then that gives us the distance to the entire solar system. Now, your activity coming up this week and next week is going to look at parallax. And parallax is a measurement of the distance to the nearest stars. And we're going to use all the information we just talked about in this discussion to figure out what the distances to the nearest stars are. But that's something that you'll be doing a little bit later.